Hello, I want to introduce you to Marko. He's a versatile engineer at Tenderly within resource and development team. Uh, research and development team. Thanks to his diverse background and his skill sets spanning to graphics programming, security, and blockchain, he contributes to Tenderly's innovative solutions. So please welcome.
Thank you. Welcome, everyone. Today, I'm going to be talking about difficult problems that we can face in generally programming, mathematics, or let's say some fields that are similar to this. I know it's called dealing with complexity, but dealing with difficulty would have been a bit too psychological. So I opted in for the complexity. So let's see what are difficult problems. There are complex problems. Oh, okay, sorry. This is the summary of what we will see today. So it's what are the difficult problems, why should we solve them, how can we solve them, and the experience in Web3, and why would we even need the difficult problem-solving skills for Web3. And if we get the time, which I'm not sure that we will, we'll try to apply some of those methods on some mathematical problem that I prepared for us. So, what are difficult problems? First of all, there are complex problems that require many different steps, but not all of them are really difficult. We can make an example of a complex problem that's not very difficult. Imagine if you wanted to go to the Tara Mountain, for example, to have a nice weekend. What would you need to do? You need to sit in the car, you need to turn it on, then do shift into the first gear, the second, third. All of those actions are not that easy. The whole task is complex. You need to watch the road, you need to watch the signs, you need to watch other cars. It's an extremely complex problem to solve, but it's not that difficult unless you're not a driver, right? So, what could be a difficult problem? Is this a difficult problem? The 102,706, whatever, multiplying two big numbers. Anyone? No? Yeah. It can be a difficult problem. In some cases, it's most of the time, even without a calculator, it's an extremely easy problem. It's just tedious. You would need to write down the steps and go step by step by step, and then do the carryover, do the sum, and stuff like that. It's really easy, but it's tedious. You would need some time, but you could get the result. But is it difficult for, let's say, a kindergartner? They haven't learned multiplication yet. Same as driving the car. It's not really difficult for anyone that has experience, but imagine being a new driver and somebody says, you need to go 5 hours driving up a mountain, and yeah, it's really, really personal if some problem is difficult or not. And it comes down mostly to it being novel or unknown. So if you have a problem that you have faced for the first time, it's probably a difficult problem. So that would be the main difference between difficult and complex problems. Complex ones are made up of different smaller entities or problems or parts, whatever. And difficult ones are the ones you can't solve or can't solve yet. So most of difficult problems nowadays are high risk, because if you try investing into a difficult problem that hasn't been solved, when I say difficult problem, I mean generally difficult for all of the people involved, it hasn't been solved yet, so it's a pretty high risk for your time investment, for your money investment. Are you putting in resources in solving that? You may end up going nowhere, but also it's a high reward problem. And why would we bother solving them? So difficult problems, why even say try it? Why not just work some, I don't know, some existing problems and solve them? Well, first of all, we reduce the difficult problem set for us personally. So you can solve something that you haven't seen before, and then The next time it's going to be a bit less difficult, and then the fifth time, same as driving. The first time you do it, it's difficult. The second time you do it, it's really difficult. 527th time, it's easy, most of the times, unless you find something like unexpected. But yeah, reducing the difficult problem set for yourself, and generally the, let's say, global difficult problem set. If you solve something really, really hard that nobody has done yet, it's a great contribution to, let's say, in our case, development or programming or whatever, or the world. So, also solving classes of problems. You often have problems that can be easily solved. One by one, you can go find solutions and do it. But if you have a class of problems, you can find some pattern and try to solve the overarching problem that will solve all of them. Those are usually very difficult. And during the process of solving problems, you can really build up your intuition. So imagine you're a chess player. You have maybe 200 games behind you. You're in some a really bad situation, you're maybe losing, and then you start analyzing. You're like, what can these pieces do? You go into the calculations and you're in overdrive doing millions of calculations, and you just can't find the solution. But for a chess master that has millions of games, he can just look at it, not even think about the position, not even like calculate one line, and he's like, oh, this is probably the best move. It's not always gonna be the best move, but you build up your intuition. It's the fast-thinking brain that's unconscious, and you build it up by solving problems of a similar class. But the bad thing about intuition, it can really be wrong sometimes. You can build it up using like simple problems. You're always doing something not that interesting, always something simple. You find some patterns, and then you stumble upon something difficult, and then you shoot yourself in the foot. You're like, yeah, I'm gonna solve this easy. I've seen this a million times. And then you postpone the project and it goes nowhere. And yeah, beyond intuition, which speeds up your work or problem-solving skills and stuff like that, you can unlock exponential contributions. What do I mean by that? You have exponential or linear contributions to, let's say, society, company, something. A linear contribution would be the contribution where you improve at doing something. Let's say a double, you become twice as good at creating television screens or something like that. And once you're double the skill in creating the television screens, you can make double the amount and make double the money. So it's linear proportion. But unlocking problem solving or solving really, really hard problems, you can go into exponential contributions. Once you solve some problem that has been solved for the first time, you can make life a lot easier for a big number of people, meaning you made a big contribution either to the world, to the company, and to yourself, whatever. And the final step, it's fun. It can be really fun, it can be tedious, it can be challenging, it can be frustrating, but at the end, once you do it, it becomes really fun. Maybe not the first few times, but once you get used to the hitting of walls and trying again, it really, really can be fun. One of my favorite hobbies is technical diving, and the core of the sport, not regular scuba diving, but technical diving, which includes like deep diving and wreck diving and cave diving. You rely on your skill to solve problems in real time, and actually you usually like depend on it. Your life usually depends on it. So yeah, it can be fun. And now, we can try to see some, let's call it methods or approaches of solving difficult problems. Most of them are pretty simple and easy, and probably most of you just do it anyways, but subconsciously. And it would be really nice to go over them and try to consciously think about it each time you try to do one of these methods and how you can apply it better. So this is just a list, and we'll go over each one of them. Okay, so question everything and black box everything. So the black box part is the first one. Once you're in a new problem space, you have a lot of unknowns. Most of the time, if it's really a difficult problem, you have extreme number of unknowns that you have never met before. That's usually the definition of a difficult problem. So what do? First, you identify all of the parts that you can. So in the problem space, like what are the parts of the problem that are required? In the input space, what is going to be our inputs, outputs, and what's going to be our solution? And quickly, but very carefully, so I put carefully intentionally there, you have to black box everything. You go through different pieces and you're like, okay, what's this? You take the inputs, the outputs, and you're like, okay, I'm gonna pretend this is a black box. It's just a process that happens, and one thing is inputted. There are some side effects, there are some outputs, and that's it. Once you black box everything, or almost everything, I would say as the first step, you should slowly start to unpack those black boxes. So this is something like in between DFS and BFS algorithm. Depth first search, you don't want to go deep into one aspect because you may not really understand it without other pieces. And if you go too wide, you may be not getting the big picture of 1 or 2 or 3 parts. So you black box everything, try to think of it as like simple parts of the problem, then you go deep into one, and you maybe have a bigger chance of understanding that one because you have everything else black boxed. And also here we have the question everything. I'm not sure if I actually, yeah, I did put the word everything. I was looking for it there. So question everything, including the problem definition. What is the problem that you're actually solving? That may be the first and most important step at all, even if before you start black boxing actually. So question, what is the problem that we are trying to solve? What are the inputs? What are the outputs? What are the interested parties? Who is going to benefit from this? Why am I doing this? And in a new problem space, every single detail is important. You can't know in advance what you can disregard, what you can forget. Then you just black box, put it in the back of your head, and try to remember it. Maybe if something else calls back to some of the black boxes, you're like, okay, let's learn a bit more. What's this process? How does it do? How does it work? And stuff like that. And also, always question the solution space. What do I mean by the solution space? Yeah, the solution that you make, like the program or the machine or anything. Always keep questioning, is this good? Can I change the problem definition to better fit the solution? Can I better fit this solution to this problem or sub-problem? So everything at every step of the way until you're done needs to be questioned. And one thing that I didn't put down here, once you're done, because, okay, this is only the first step, but once you're done, a few steps after this, you really should write down your solution or try to explain it as best as you can. So later when you return to the same problem, you can actually remember the process that brought you there and much easily understand like what are the steps. So we usually call it documentation. Yeah, so question everything. This is a small example from some problems that we were having with our debugger. Tenderly makes a debugger for Solidity. And has anybody ever used the debugger? I have. Has anybody ever written a debugger? Yeah, and what's the process? How would you explain it in one sentence? Horrible, right? Yeah. Writing debuggers is extremely horrible because what you have to do, you have to match the compiled bytecode, so the machine code that the machine executes with the source code of the program. And some compilers really don't give you good helping tools to do that. Solidity is one of them, unfortunately. Solidity is one of the main languages in Web3 for creating smart contracts, and it basically gives you nothing. So you have to pattern match, you have to scribble around, see what's actually doing what, go step by step, create patterns, and then you end up like me, like with 10 papers of bytecode printed out on the, what's it called, table, and this on the whiteboard. And you can see how many instructions here. It's like a full whiteboard of instructions. And this is an extremely complicated function, which is basically x is equal to 55, if I remember. Yeah, it's an execution of setting one variable to 55. It's extremely horrible, but what you have to do is find underlying patterns and solve it step by step and question each of the instructions, because you have no idea if it will create a side effect that actually helps you solve the problem. So yeah, you have to be like a conspiracy theorist sometimes. The next thing, after questioning everything, we usually, for complex problems, need to simplify or subdivide the problem. Subdividing into smaller problems can often lead to increases like in productivity. You can solve one of them at a time. You can then figure out, how can we put all of this together to solve the general problem? So smart combinations of simple solutions can give you faster and better outcomes. The problem there is you're never sure if you subdivide it correctly. So back to the first step, always question everything. If you subdivided it one way, like on user level, which are the different groups of users you can subdivide onto, or what are the different inputs, or what are the different stages, maybe think about it, maybe subdivide in a second category or something like that. Also, incremental solutions, try to find some starting point, maybe a simple problem or sub-problem that you can build upon. This is how we built up our compiler. We started building up, not compiler, sorry, debugger. Started building up small heuristics one by one, detecting some errors first, then detecting some jumps, then function calls, then loops, and then you take a lot of small increments and actually create a pretty good solution to a difficult problem. And next to subdividing, a good tool can be simplifying. And by simplifying, I mean trying to solve a similar problem that is less complex or less difficult. So an easy example could be, can you solve a 3D problem in 2D first? You have some complex 3D problem. Let's say you work as a graphics engineer at some game company, and you're trying to do some 3D effect, and you can't do it. Just do it in 2D. Even if it's useless, even if it can't be upgraded to 3D, you're going to learn a lot. You're going to have some experiences. You're going to see what's important, what's not important, and then skip it. And then, yeah, apply it to 3D. Can a problem be solved for specific cases? Yeah. Can you try to isolate specific cases, simplifying what you're trying to do? If you solve some specific cases, let's say you have 10 different user groups or 10 different inputs, can you solve it for one? Just one. Don't care about anything else. If you do it, maybe you'll learn something new. Maybe the parts of the problem are going to be more known to you, which means the problem is less difficult. And incrementally, you can solve it. Also, you can think about having different representations, especially if you're doing something in mathematics, cryptography, geometry, and anything that's numbers-based. Can you make a different representation of the number, of the coordinate systems, of whatever, of how you store the data? Maybe like different storage methods can vastly simplify your problem. And can variables be added or removed? By variables, I usually mean like inputs and outputs. Can you maybe cut down one of the inputs to make the problem a lot simpler? Maybe you change the problem that you're trying to solve. Maybe you just solve for an X input and then you add it back later. But think about that simplification. Can you remove something to make it more easy to solve, or can you actually add something? Often you have the case, okay, I have this problem, it's really hard to solve, but if I add this component as the input, it can do some stuff. Okay, next one. I'm going a bit faster because I have a lot of stuff to cover, and I want to show you a small demonstration at the end. So find patterns. What I mean by patterns, anything that repeats itself in the problem space, like if you have a problem that has some different requirements that seem similar to you, try to find a common solution for them. In the input, once you have an input for the problem, you can try to group it in various ways. Try to group it by users, try to group it by anything you can think of. Output, you can also see, like, once you solve the problem or partially solve it, you see some outputs, and if you see some outputs repeating themselves often, you can try to figure out, okay, what's causing this class of output? Let's try to solve that perfectly, and then we can go carry on to something else. And also the solution, and I think this is the most important part. I think this is the part that you're all familiar with. You're writing some program, you're writing some solution, creating some machine, and you often find yourself creating the same thing. Once you do that, you don't want to continue like doing it again and again and again. You have to figure out, okay, what's the pattern that's causing this specific code, or what's the pattern that's causing this specific thing that I have to do every time, and see if you can solve for that. And yeah, finding patterns in similar or solved problems can really be a good way to do that. You can go and check, yeah, I have a problem. Let's think about it. What's similar? Am I doing something in the automotive industry, something like self-driving cars? Has this been figured out in the airplane industry? Do airplanes actually solve this? Do boats solve this? Try to check out like other spaces that have similar problems and see what their solutions are. And yeah, patterns greatly simplify complex problems. Once you find a pattern, especially like in the debugger case, you find some pattern that always occurs, that can really, really simplify your problem, and you rely on that pattern as a starting off point and build up from there. Yes, this is the most ethereal approach, I think. It's really hard to explain, understand, or let's say demonstrate. I'll try to demonstrate it later. A useful perspective shift. So one of the easiest perspective shifts you can do is the perspective shift of other people's points of views. Don't just think about it as a developer, go at it as a user, go at it as your manager, go at it as anybody else. Try to put yourself, okay, if I were to use this solution, would I be happy with this? And also, that includes explaining the problem to some other people. You've probably seen this happen at the office. You have something you can't solve, then you go to some other colleague, and let's say that colleague is the same skill level as you. He won't solve it because he's better, but you try to solve it together. And then you explain the problem to the colleague, and then he gets stuck, or she gets stuck with you at the same point. What's happening here? You're usually looking at it from the same perspective. You're usually like explaining it to somebody that has a similar problem-solving skills to you, and maybe you gloss over something that's really important. Maybe you're like, this does that, this does that, blah, 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 done. And no, he doesn't understand, or she doesn't understand what's the underlying problem, and you don't discover it yourself. If you try to explain the problem to different people, extremely different to you, go explain it to some of your parents and see how it goes. You have to go really, really deep and really specific in order for them to understand. You would have to chop up the problem into small chunks and then explain every chunk to them. And this is actually what Feynman did. I put it basically because of him. He would go, Richard Feynman is one of the big physicists from USA, and yeah, he would go around, talk to the cleaning ladies at the university. He would go talk to the cashier at the traffic or the shop across the university and try to explain it in layman's terms, what he's trying to solve, and this would bring him a new perspectives on how to solve the problem. So this is the easier one, and the harder one is shifting perspectives within the problem space itself. Once you find something that's really useful, let's say some shorthand that allows you to solve a part of the problem, you can try to think the whole solution or the whole problem statement from that point. Can I rearrange the problem statement so it fits this very useful thing that I have found? I'll try to demonstrate that thing, and those are the last two ones. So shifts in the perspective of new things and shifting the perspective of the problem definition itself to actually fit the things that you found useful. And the last one, that is the simple, try to persevere. It can be really discouraging. You can work on a problem for days, weeks, months, but once you start solving it, you don't even see the progress. I have been solving some difficult problems in a company that I worked for. I actually have here one colleague from the game studio. And one day the studio decided, game development studio decided to put me on solving flickering issues in the rendering engine. And I cracked my head for a month on a simple flickering problem. There was some object that was appearing and disappearing and appearing and disappearing. And there was zero progress. You couldn't see anything. But actually, without me actually knowing it, I was making progress, but I just couldn't see it. It's like solving a murder mystery. You maybe see a raincoat there, maybe you see some steps over there, but those are not progress. You just saw a raincoat. But maybe later you find out that that raincoat has actually been included somehow, and you did make a progress by acknowledging that it exists. But you didn't see it as progress because it wasn't relevant at the time. So unexpected sources of progress can appear like that. You maybe overlook something that's not important at the moment, put it at the back of your head, and you're like, okay, I'm not making progress for 2 weeks, and then bam, like 2 days after that, you realize that's the key to the solution. And that's the point. The last piece of the puzzle actually ties everything together, and you can actually understand that you did make progress all the time. Yeah, so persevere, try not to give up. And how do you give up? That's not a thing that I'm really good at. I did give up many times, but I'm not sure if I should have, or I maybe persevered too long, but try to persevere if you're trying something really difficult. But what does this have to do with the blockchain? We'll go over this quickly. The blockchain, or Ethereum specifically, because we are usually at Tenderly focusing on Ethereum or similar blockchain variants, you have a unification of many interesting problems. You have many interesting fields working together. So you have a lot of problems from many, many different fields that you can access at the same time, and maybe in some combination solve them together. And here you have a list of the usual stuff. Cryptography as the base of every blockchain. Of course, the distributed systems. You have to keep the ledgers distributed. Security, everything has to be secure and fraud-proof or tamper-proof or whatever. Of course, you have programming, which is basically covering all of these as an underlying, let's say, field. But yeah, you can access many different things, you can reach many different people, you can reach many different problems and try to solve them. And also Ethereum, or Web3 in general, is a really young industry. It's still in the forming years. You have a lot of impact. There are a lot of unsolved problems. There are a lot of opportunities that you can cash out on, that you can solve either for profit or for, let's say, whatever, bling bling, fame. Yeah, and there is a lot of unique people that are really, really motivated. You have extreme experts in cryptography, and they're really different from one another. You can see like very, very different people, from hillbillies that do crypto to like furries that openly walk around, and it's really interesting to interact with them. One of my favorite archetype of people is the security anonymous guys. You meet them in real life, they just give you their handle. They don't give you your name or number or anything. They just exist as a handle or username or whatever. And there are lots of challenges. Some of them are good, some of them are bad. The space is a bit disorganized. You can often find some scams or false information or stuff like that. Those are the problems that are not really good. They're not hard, they're just annoying. You try to Google something, you find some scam, and you're like, but why? Just stop it. So yeah, Ethereum or Web3 in general is great for problem solving. And an important thing here is to mention it's really great for like normal developers. You don't have to develop smart contracts. You can actually try to develop libraries that other people use. You can develop tools. You can develop different blockchains. You can try to advance the cryptography scene and stuff like that. But yeah, I think we're going to skip the Q&A parts, if that's okay, so I can show you the mathematics problem and maybe try to explain it in 4 minutes and 40 seconds. Okay, here we have a problem that's really, I think, the 12th problem of Putnam 2005. Putnam is a mathematical competition for students, and it's extremely difficult. You have 12 problems, and each of them has 10 points, and that's 120 points, and the median score, I think, is like 2 points. So the best of the best students manage to make 2 points, and each consecutive problem is more difficult than the previous one. So this is the 12th problem of the 2005 competition in mathematics, and we're going to actually try to solve it. And what's the problem? If we have a sphere or a ball, or however you want to call it, a 3D circle, 3D object, and if you choose 4 random points, uniformly distributed, when I say uniformly distributed, I mean they can end up anywhere with the same chance, what's the probability that this center point will be included as the part of the pyramid that is formed? You see these 4 points create a pyramid. Here it's upside down, but it's still a pyramid, and it does contain the point C. So how can we solve it? Yeah, really hard. Without applying some of those methods, basically impossible. The first one would be to simplify. Can we solve this in the 2D case? The equivalent 2D case would be choose 3 points in a circle. What's the probability that this triangle will contain the spot C? And we can think about it, try to see what are the different triangles that can be generated, maybe do some surface integrals, maybe do some probability densities, but it's too much big math words. So what do? We have to simplify, but more. Let's say we have 2 fixed points, P0, P1. If we choose a third point that forms the triangle, what's the probability that it's going to be that the triangle will include C? Again, another simplification. We can subdivide the problem. How can we do it? We try to imagine this. After testing many different triangles, we maybe realize that these lines that go through our original points and the center of the circle actually mean something. Because if you imagine, you have this P0, P1, and you go below this, P0 and P2 will form a triangle that goes underneath the C line. Simple, also the equivalent is above. If you go above the P1 mirrored, you're gonna miss the center because the other point, the bottom line of the triangle will be above the C line. Sorry, C point. So you have 4 distinct cases. Of course, this one is trivially easy because the whole triangle will be here, so it's not in the middle. You have this one, you've seen that, it's above. This one possibly is gonna give a good solution. This one we see it's underneath. So what are the useful cases? The useful cases are on the line. If we draw the triangle, it's pretty obvious. The C is inside the triangle. So we have a useful solution set. But what's the probability that it's going to happen? Here we would have to spend like 10 minutes trying to decipher what's the probability. The probability would be the length of this arc divided by the whole circle. And you have to find out what's the average size of this arc. we're going to skip that calculation, and I'm going to tell you it's 1/4. So on average, this will be 1/4 of the circle, and then you'll have 25% chance to generate. So we go back to the 3D case. What do? We try to generalize, try to find the same thing. 3 points, three lines that go through the middle, and then you calculate the average size area of this oblique triangle. And how do we do that? We can't really. It's, again, really too hard because, yeah, you generalize to 2D, but it doesn't really translate to 3D because how do you calculate this? It's really, really hard. What do? You take the original triangle that you managed to find the solution, and you try to think, what's the useful step that we made to make this problem solvable? It was these 2 lines. So you try to shift your perspective around those 2 lines. So you maybe start thinking about the problem differently. I'll state the problem in a different way, but it will be the same problem. So we are going to choose we're first going to choose 1 point, the 3rd point that we chose at the end last time. Then we're going to choose 2 random lines. And then for that line, for each line, we are going to choose 2 points. You see, we have like point P0 can end up here or there, P1 can end up on the left, on the right, on the left, on the right, okay? So this gives us 4 distinct solutions, and only one of them is okay. So we here don't have to think about the area of the triangle. We have 4 distinct solutions, or 4 distinct triangles that can appear, and only one of them is okay. So we have 2 dimensions, which have to have 2 lines to be created, which is 2 squared, which is 4 options, which is what result? 1/4, which is 25, right? The same that we got from the area approach. And if we try to generalize into 3D, to do the same, we would have to pick the point P3, pick 3 random lines, then toggle one or the other, do a coin flip, whatever, and then we would get 3 dimensions, 3 lines, 2 to the 3rd options, which is 8 options. And what's the solution to the problem? Anyone? Come on. From this one, it's a bit easy. It's 1/8. It's just 12.5%. Yeah, so why do we bother? It's fun. Has anybody enjoyed this problem? Is it something that you would try yourself? Probably, maybe not. Maybe maths is a bit too abstract. But one thing that I would like to ask you is if you are interested in solving difficult problems, take a look at our developer diaries. This is a blog space that I started intentionally. I wanted to give our developers a space to put their stories, to see, like, we have an interesting problem that we solved. Okay, put it in developer diaries. So a lot of people approached me. They said, hey, look at this. This is so fun. And I'm like, why don't you write an article? And we did start writing articles internally and tenderly. We had a newsletter for our company. Hey, look at the cool problems that we solved. And then we started adapting them to like a public blog space where you can find maybe not always difficult problems, but interesting problems that we managed to solve. And yeah, that's it from me.